So welcome all. I am Pintu Kumar. I'm a PhD student at IUR IIT Bombay. So this is a tutorial session based on week 1 content covered in the course Introduction to Machine Learning that is being originally taught by Professor Bhuveshna Sarkar. So this is a basic kind of tutorial to clear your doubts, and you can ask your questions, and I'll try to cover like some basic aspects of topics taught in week 1. This won't be I won't be explaining any theory as such here. I'll just be discussing an outline so that you can ask your doubts. So you can turn on your mic anytime you want, or you can type it in the chat box, whatever way you feel comfortable. So people are still joining us this platform. So in this tutorial, I'll try to cover two sections, that is linear regression and decision tree. These were two major sections covered this week. So somebody's microphone is on. It would be good if you can turn it. Thank you. So linear regression is the first machine learning algorithm that is being taught in this course. So I'll go slow about it. So first of all, this is a supervised learning algorithm. So you all came across what a supervised and unsupervised algorithm is. So this one falls into the category of supervised algorithm. You are already given with data points of type xi's and yi's. So you have features as well as the prediction that you have to make. This can be label or some regression values. So you have both these quantities available. So like if you recall, there were basically two kind of tasks that we had. One was classification, another one was regression. So in classification, you had to predict out of some classes. So you had some discrete values to predict from. And in regression, you have to predict some continuous value. I'll give an example what an regression is just to refresh your memory. Let's say you want to write a code to predict housing price. So you give your program input, what's the size of that house, number of bedrooms probably, and other thing that might be important is locality. And based on this quantity, it would give you an continuous price of the house. It should output the price of a house. Okay. We'll begin with linear regression. So what do we mean by linear regression is, like, let's say you have these red data points that I'm marking now as blue. So you had these data points. So these are the X values that you have, and these are the Y values that you have. These are Y, and these are your X. So given your X value, so these X right now is just a one-dimensional value, but in practice, you come across these X as vectors, which is difficult to plot on the piece of paper, so I'm not plotting it here. So people are joining. Yeah. So what you have to do is, you have to learn a function that can give you f of x when you have given x as an input. So you have some data points. You already know what's the value of x that you are getting at 5. Okay, and you know what the value you are getting at 7 via these red points. You want to fit a best line that can predict. So what you want to do is you want to learn a function f of form ax plus b, which has the least error in this case. So what do I mean by least error is something like this. So if you have, let's say, the actual value was something over here, and your function is given this, so you are making this much of error at that instance. So when you sum up all these errors, you want the error to be least. So this is what you want. So if you look at a generic class of linear function in one variable, it is of type ax plus b. So you want to learn the values of a and b so that your functions best fit to the data. So this is our task at hand. Now, this linear function might seem very easy and a like simple function, and you might think that this might not sorry, this is for week 2. Thank you, Akshay. Yeah, this is for week 2. uh, yeah, so what I was saying, yeah, the linear function might seem pretty simple, but with some modification that I'll come later to, like with some modification, you can like fit in complex function with the help of techniques, whatever you are developing right now. Okay, so you just need to incorporate some non-linear features that will help you fit linear curve, like fit linear curve and get complex function out of it. Another thing is, because this is linear, so it is quite simple to train and do all kind of calculation on top of it, analyze these things. So it is simple to do those kind of things. So like that. Now the next thing is what kind of error or the loss function that we considered over here is error or loss function is. So if you look at this figure and you want to take, let's say you have some data point x1. So x1 over here can be 2. Okay. So you expected the value of 2 to be something around here. So I will tell you what so yeah, so 2 for 2x is 2 and y is 19. And the function that I fitted to it, that is giving a value of f of x is equal to 15. So error over here, you can take f of x minus y, so it would come something like -4. So when counting error, you might have came across this in class 12 physics or anywhere. Whenever you count error, you tend to take absolute value of error. Otherwise, they will cancel and error would make no sense. So for similar approach, we have two options over here. So one, we have multiple options, but two common option is taking mod of error, or we can take squared error, right? So in linear regression, we go for squared error. So there are multiple reasons to it, but one simple reason that I can point to you is like these kind of functions are not differentiable. And when we try to find values of a and b, we tend to use technique that want this loss function to be differentiable. Okay, so for this reason we use this. There are other reasons also, but right now just know that this is the one of the reasons why we use squared loss function. Okay, so let's say we have some f of x, then you have to estimate this value of a and b so that your fit is best. So now when you look at, if you, let's say you have n data points from x1 to xn, so how does the error function look? So this j denotes the error function that is based on the parameters a and b. So if you vary a and b, your f of x would vary, and hence the value of j would vary for you. Now, when you look at this formula over here, so what is happening, you are evaluating the value of f of x at every point. Then you're looking at the true value. You're taking their sum, you're taking their difference and summing up their squares, right? So this is as like intuitive. Now, why this 1 by 2 n term over here is like this 1 by 2, when you take derivative of this function, I'll tell you why do we want derivative over here. Now, when you take derivative, this 2 goes in like in front. So it makes calculation a little bit simpler. That's why we take this 1 by 2. And this n term in the denominator is to normalize the loss. Now, let's say you are training a model with, let's say, some 100 data points and training other model with 1000 data points. So if you don't normalize this loss, then this like if you keep summing over 1000 data points, then this loss tends to accumulate and grow large, right? Even like at specific instances, let's say at every data point, this is giving lesser loss than this, but because number of data points are high, it tends to grow large. So that's why we kind of normalize this loss so that we can compare two different models. It is easy to compare. So just to sort of summarize till now, so in linear regression, what we have, we try to learn a function of form ax plus b, To do so, we have defined a loss function of this form. Now we want to find values of a and b such that our j of a b is minimum. Okay, so this is something that we have, okay, that we want to do. Now, before moving ahead, this like the main goal of this kind of tutorial sessions is to make you like comfortable with the assignments that you have to attend, like weekly assignment that you get. So this is a question from previous year's assignment. So I would like you to attend based on the like whatever we have discussed till now, and we can verify the question. So like you can try. I'll also discuss later on. So you can try and just type out the answer in chat. So the question is, you have some values of x, some values of y, and the cost function or the j. This cost function is also known as the loss. Okay, so this is given to you. Now the like the way I wrote this a and b, you can write them as a vector a and b and name it theta. So this is theta is nothing but a vector a comma b. So you are getting this kind of loss function. Now when your theta is 2 comma 1, they are asking you to give the answer. Now see that this theta naught is the intercept, not the slope over here. You can attempt this question, I hope. I'd like to see some of the answers in chat. If you have any doubt, also till now you can feel like you can ask me. Anybody tried solving this? So this h theta or f of x is given to us, right? So h is 2 plus x. Let me also solve. Others might verify whether Tanmay's answer is right or not. So I'll also solve. Okay, so h we have given theta equal to 2 comma 1. So if you put in theta not equal to 2 and 1 over here, you'll get h as 2 plus x. So if you evaluate h of x over here, this is nothing but 8, 7, 12, and what do you get over there? 5. So now you have to take the difference between them, take their square, and sum them up, right? So I think this would be easy for you also. So this would be 1, 9, again 9, and 1, right? So if you sum them up, it is 20. And you have a factor of 1 by 2m. So m is the number of data points. Same was n over here. So if you take 20 divided by 2 into, there are 4 data points, right? So you will get, what do you get? 10 by 8. Oh, sorry, 2 into 4. So 10 by 4, it is 2.5. Were others able to solve it, or just Tanmay was able to do it? If you have any doubt about this, please feel free to ask, because this is a very basic model. And if you are not clear with technicalities over here, it would be difficult for you to follow up lectures ahead.
Sir, how we got these values 1991?
Okay, so I'll just do it. I'll just. So whoever asked this, see that we wanted to find a function f, right? So here they have defined that function to be h. So this is just a change of notation. So
Okay,
you
sir.
have to find h of x. Now what is h of x? They have given it to be theta naught plus theta 1 of x. Okay. Now theta is mentioned
Sir.
over here. Theta naught is your 2. So this h becomes 2. And theta 1 is x. So your h of x is 2 plus x. Now when you put in x is equal to 6 in this, what do you get? 8 over here.
8.
Okay.
Yes,
Similarly,
sir,
you get
these values are clear. 8,
okay.
7, 12.
Okay. Now what you have to do according to the formula is you have to take the difference of hx and y and square it, right? So if you take h of x minus y, what do you get over here? This is 1. Oh, I'll use some other
Okay,
color.
sir. I got it now.
Okay, so others also I think would have. Paritosh, is it clear for you now? So if you take h of x minus y, it will get 1 over here, 3 over here, 3 over here, and 1 over here. Then you square it and then sum it up. You will get 20. Then you can divide it by 1 by 2n. So this is how like error is calculated in any machine learning algorithm. You compute the error at every point and then you sum it up and then sort of normalize it, right? So this error would vary from different models, like they vary from model to model, but the generic idea is same. Okay, so you have got an error at one fixed value of theta, right? But our goal is to find Paritosh, was it clear for you? Sorry, Preeti Ghosh. I'm sorry, it was not Paritosh. Preeti
Yes,
Ghosh
sir.
was
Yes.
okay. Thank you. So our goal is to find the theta which would minimize j for us. Okay, so we don't want any theta, but we want theta that will minimize it for us. So like if any one of you would have done any course on optimization, they would know that when we have a, so over here, the example that we considered, x was a one variable vector. So it was just one variable, x was. So in practice, what we get is this x is generally very long vectors. So these are some, let's say 20 dimension or 100 dimension or even larger dimension vectors. So you generally get larger dimension vectors. So this f is a function of some vector. I'll just make it bold. And you want to minimize this function, this j theta. So j would also now be a function of some a1, a2. I'll just give you an. So let's say your x is x1, x2 till x20. Then your f of x would be a function like, so your f of x is a function like a1 x1 plus a2 x2 till a20 x20, something like this, right? So now your this j would also depend on, so you will have one more free variable also, some, let's say a21. So will depend on some 21 variable. So this is not a function in one variable. So you can't just simply take the derivative and put it to 0. This is not possible for j, right? So, and also like this, even if you do this kind of thing, like in higher dimension, you take partial derivative and take it to 0. This might not be very easy to solve and verify whether it is a minimum point or a maximum point, because in reality, these curves that you get are not very smooth. There would be many local minimas and those kind of things. Okay. So yeah, coming back to the point. So there is a sort of theorem, or you can say a fact in optimization you might have came across. Like if you have a function in a multiple variable, let's say this x is x1, x2, x3, then you can define a quantity called a gradient. Okay, what a gradient is denoted something like this. This is represented as, so its first element, this is a vector, gradient of j would be a vector. Its first element is partial derivative of j with respect to x1. So like if anybody don't know what a partial derivative is, please refer to some resource to get yourself acquainted with it. And second element would be partial derivative of j with respect to the second element. Similarly, you will get a vector out of it. Okay. So something like this. Okay. Now, what this gradient is, this gradient would give you a direction. This gradient is also a vector. So this gives you a direction. What the fact is, what fact it is that that this gradient is the direction of maximum increase of a function. Okay. Increase of a function. So if you have some function, let's say, so this is your 2D plane and your function would lie something on top of it. So if you are standing at a point, let's say this, and you got a gradient to be this direction. So if you move in this direction 1 unit, so you'll get maximum increase in function value as compared to you move in any other direction 1 unit. Okay, so if you move by a fixed amount of distance in this direction, you'll get maximum increase. Okay, so we want to use this property to find minimum for our j. Okay, so like if the maximum increase in this direction, it is known that the maximum decrease would be in opposite direction to this. Okay, so what we do over here is, I'll just, sorry, I'll just do one thing. Yeah, so I'll take an example over here. So if you see here, this is a function in one variable. This is x, this is y. If you take derivative at this point, right, it would be positive. So positive derivative means this would point in this direction, whatever it is. So if you are standing at 2.5, if you take derivative over here, it is pointing in this direction. So in one-dimensional plane, there are only two directions possible. It can either move left or right. If you are standing on number line, somewhere here, you can either move right or you can move left. So at this point, if you move in direction of the derivative, because partial derivative in one direction is nothing but the derivative, then your function is increasing. This fact you all know that if f dash x is greater than 0, your function is increasing at that point. Okay. Yeah. So the same thing is true in multiple dimension as I mentioned. So what we want to do is we want to move in opposite direction. Let's say we are standing at 0.7.5. So we found its derivative. It is pointing towards this side, that it is increasing over here. What we want to do is we want to move by a certain length in the opposite direction. Okay. So we will move something over here. Let's say we came across over here. Again, we calculated the derivative. Again, we saw that it is increasing over here. We will move again by some distance. We will again come here. We'll see that it is decreasing. We'll again move something over here. Now again, we'll move here and then we'll finally sort of converge to the minimum point. So this is the idea that we are going to follow in some 2-dimension also. So what we are going to do is, for every parameter, we are going to update it via the same rule. So like if you will look at this, so the j was the function of a comma b. If you look at gradient of j, it would be del j by del a, right? And the second component would be del j by del b. Okay. So for the first variable, you will move some alpha times this partial derivative. Okay. Right. And for the b thing, you will move some alpha times this second coordinate of this gradient. This way we'll update a and b, and till when will we be updating? Till the time we reach some convergence point or some stopping criteria. Your stopping criteria can be that your gradient has grown very small. Okay. So other thing can be like the a and b that you are getting, they are very close to each other. Okay. So you got a1, b1 in one epoch, again then you got a2, b2. And the difference between these two vectors is very small. Then also you can, so whatever I'm telling you, these are like important from implication point of view, not very theoretical. Yeah. So this is how we kind of learn this thing. Okay. So to summarize what I said just now is, so for like you have a loss function a comma depending on a comma b, you will update your a based on a minus some alpha del j by del a, and your b based on alpha del j by del b. Okay, if you had this function as a function of more variables, let's say x1, x2, I won't use x1, x2 over here. Let's say this is function of w1, w2, wn, then you will update every parameter in same manner. So you will take W1 is equal to W1 minus alpha times del J by del W1. Okay. And similarly, you will take Wn is equal to Wn minus just a second. Yeah. So alpha times del J by del W. So the gradient, okay. So first I'll answer the second question that has been asked. So gradient is the vector that you obtain when you take partial derivative with respect to a and b. So whatever you have asked, so the first component of this gradient is calculated with respect to your a, and the second component is calculated with respect to b. And to answer your question, Akshay, so they are like the update is made after we have like updated all A and B. So let's say you're standing over here, then you want to move in from here to here, right? So it's a direct move from here to here, nothing like that. You move in X direction first, and then you again look at Y direction. This is not like this. So this is another method that is possible. But in gradient descent, we first update both A and B, then move to a new value of A and B, and then calculate the error. So it is done simultaneously, not one after the other. Okay, Akshay, is it clear? Whatever I said. Okay, yeah. So now, like any other questions you have, like, so Akshay, whatever you ask, if you do a optimization course, you would know, like you can do optimization is a good tool to learn machine learning. So you move straight away in this direction, and you can also move like first in along the x-axis, then along the y-axis. But this gradient descent is in some sense better also, and the method that we're using is this. So anybody else has any doubt till now? So these are some important things. Any doubt? Okay. So one more important thing that I wanted to mention to you guys was that how do we choose alpha? Okay. Now you saw that over here also I mentioned that starting from here we'll move some like with some value over here, and we'll reach this point, then we'll move. So how much we are moving is dependent on this value alpha that we are getting. Okay. Now how do we choose this alpha? Let's say I chose this uh, alpha to be very, very small. Okay. So I started here and I chose my alpha to be very small. So it will take very tiny step, it will reach here. Then I'll take very tiny step, it will reach here. Then it will take another tiny step and reach here. So it will take a lot of time to converge, right? Even if it does converge, it will take a lot of time to converge. Let's say my function has a small pot like this. So this is a smooth x square function, but in real world, when you look at this data or the sort of manifold generated by this data, you don't get very smooth curves. You will have something like this. Let's say this curve had some like this went down over here. Now, when this uh, when this update will reach here, this will sort of reach here. Then we will see that the gradient over here is 0, and it won't make any further updates. So taking small steps, you can also get stuck in local minima. So you can get stuck in this kind of pot and never you reach your global minima. So this is a problem with taking small alpha. Now, let's say that there is a problem with small alpha, I'll take alpha to be very large. Now, if you take your updates to be very large, what might happen is, so this is one example that I drew, but another example can be you can finally reach from here to, let's say here, straight away. Then you sort of again jump till here. So you might never converge, right? So here is another example where I'm not taking that big a step. I reached here, then I reached here. I sort of reached here and then again jumped here and then again jumped here. So I never visited this region because my alpha was very large. So the question is how to choose alpha. Okay. So there is not a very at least in practice, theoretically you can find a good value of alpha that you might learn in some optimization course and those kind of thing. Theoretically it is possible. Practically evaluating alpha at every point is not a great idea. So practically what we do is we treat alpha as a hyperparameter. Okay. What do we mean by hyperparameter is, so this parameter we are not giving to the algorithm, like we are not fixing this alpha. We don't know what this alpha is for fixed. And we don't want to learn this thing. So this A and B that we had, we were learning this A and B. But alpha we don't want to learn. So what we do is, so you might remember that we had came across a concept of validation set. So validation sets are useful to tune, I won't say train, to tune your hyperparameter. What you do is you take some value of alpha, you see how your how your model is performing on this validation set V, let's say how your model is performing. Let's say you took 5 values of alpha, alpha 1, alpha 2, alpha 3, and alpha 5. You took it to be 0.1, you took it to be 1, 0.01, and something like this. Then you say on what value of alpha your model is performing best on the validation set. And based on that, you choose your alpha. Okay, so this is how we do things. So any doubt till now? I'm covering pretty simple things today, but yeah, these are important. Okay, so this curves, what they are showing is, what I try to show is, like this earlier curve, I tried to show that when we have very small steps, I'll tell you where do we get our validation set from. So when we take our very small steps, there is a possibility that we might not reach here. And what this curve is showing is, like if we take very large step, we again might not reach here. So via these curves, I was trying to show that like what is the problem with small and large value of alpha. Okay, so the next question is, where do we get our validation set from? Okay, so Pramila, what we do is, so whatever data set we have, let's say we have this much of data set, you take around, let's say 70, this, again, this value is something that you have to fix. It is not some rule that you have to follow, but we take a large chunk of it to train our model. So this is called a training data set. Then for the rest data, you can sort of divide it into two. You take first half to be the validation set. Okay. And the second half you take to be the test data. So this is how we get our validation data. So you divide your data before training the model to get the validation data. So in linear regression, I don't think, Akshay, there is any hyperparameter that you need to worry about right now. But in more complex uh, like uh, models, you will get more hyperparameters that you have to tune. Let's say in deep network, you have something like dropout, or even the parameters associated with momentum. Like when you go to complex model, you'll get more hyperparameters, but right now you have only one to tackle. Okay. Yeah, so this is a good question, like whether a tuning alpha with the help of validation would an overfitting occur. See, yes, in some sense you can say that you would be overfitting to validation data. Okay, so I'll give you an example to validation data. You can say that there will be overfitting. So let's say you chose alpha is equal to 0.1 and 1. Okay, you saw that it is performing well on this, so you took some value around something like, let's say on the next step you took something around 0.11 and 0.12. Then you again went on fine tuning it to get your precise value of alpha. So doing something like this would certainly overfit to the validation data. Okay, but generally in practice, the dilemma is not whether to choose 0.11 or 0.12, like you have to make, in practice, you have to make choices between whether to choose 10 to the power 2 or 10 to the power minus 3. Okay. So when you are making choices which are very far apart, in that case, you don't see overfitting because of this checking on validation data. Yeah, like if you fine tune your alpha a lot based on the results that you're getting on validation data, then of course it would like sort of overfit to it. Anything else? Okay, so
What is the criteria of overfit or underfit?
okay, so there is, I won't say a very precise definition, but I'll just give you like how can you know your data is overfitting. So let's say you learned a function f. Okay, you learned a function f using your training data, and you know that you have some other function h which is performing uh, poor on your training data. Like people are still joining. Yeah. So the performance of h on training data is better than that of f on training data. Okay. So on sorry. So the on training data, your h is performing bad when compared to your f on training data. But when you're using your testing data, this h is sort of performing better than your f on test data. So because this test data is sort of unseen sample, then you can say that your h has sort of your f has sort of overfitted to your training data. So it is like kind of stuck to your training data. I hope that. So this definition is something that Professor Sudeshna Sarkar also mentioned. So yeah. Okay, I'll move ahead. So like there are three types of basically these are not basically types of gradient descent, but how do we implement this kind of like how do we implement gradient descent? So these types are based on that. So first of them is called batch gradient descent. Now, what do we mean by batch gradient descent is, so you had update rule something like this, okay? And if you remember, your J was something like this, okay? Now, so this update rule for A can be rewritten something like this. I'm just putting in the value of J over here. What you see over here is while calculating this J, you're taking summation over all the data points, error over all the data points, and then updating your this function, right? Now, so this is something what is called batch gradient descent. So while making one update for this A and B, you are looking at all the data points and then decide. So error on the first data point, error on the second data point. You are looking at all the data points and then deciding upon the uh, what update to make. The second, completely opposite to this, is something called stochastic gradient descent. Okay. What you do is, rather than taking this sum over here, what you do, you update for one data point in a go. So what will you do is A minus alpha del by del A. So 1 by 2 and won't come here. Then it would be f of x1 minus y1 square. So something like this. Okay, so you just look at one of the data point and you make the update based on this. Similarly for B, then you move to the next data point. Okay, so you look at one data point at a time. This way, what you get is called your stochastic gradient descent. Okay, so this sometimes help you jump over the local minimas. Okay, and if you have compute scarcity, so this summation, holding the summation will use your compute resources. So over here, you just want to have one data point, you update based on it. So this is another thing that is useful over here. Third one is mini batch gradient descent. Okay, so what you do, this is something in between batch descent and stochastic gradient descent. So over here you split your this training data set in, let's say, batches. So you have batch 1, batch 2. So you train your J first on batch 1, update A and B, and then you train on batch 2. So this is what we do over here in mini batch gradient design. Okay, so I had included one more question, but I'll skip it because I have very less time and I thought I'll cover something on decision tree also. So anyone has any doubt on linear regression, I'll try to answer this. I'll wait for a minute or two for you to ask anything that you have on this. You can type it out in chat or you can unmute yourself and speak.
Sir, there is a question in week 2 assignment that the output of linear regression is. So, like we know it is continuous, but what is always lies in a finite range? I'm not able to understand.
Okay, so just one thing is that because your week 2 assignment is part of like it is a graded assignment, so I am simply not allowed to tell you the exact answer. But I think your question is sort of conceptual that you want to ask. So I haven't seen the week 2 assignment. Can you please tell me the question that you're exactly asking so that if there is something conceptual, I can tell you. Like
So
I
the,
haven't seen the assignment, so that's why I can't say.
the question is like in linear regression, the output is so discrete, continuous, and always lies in a finite range, and maybe discrete or continuous.
Okay, so like when you look at this, when you generally look at the broad classification of this classification and regression, okay, and regression. So your classification generally gives you discrete values, okay, and regression gives you continuous values. So what do like I mean over here by what do they mean by this in a bounded range is, so let's say you train a function f. What in linear regression you will do? You will train some function f. It will give you some y output, some output. What it is saying is whatever input you give to this f, it will lie between some minus m to m. Okay, some large number. So let's say it will lie between minus 10 lakh to 10 lakh. Okay, this is what it means to be bounded. I can't tell you the exact answer to the question because it is graded and this session is being recorded. So, but
Yes,
I
sir.
can tell you what this means to be bounded. So your values, whatever you are getting, is within some like bound. So you know, it is less than some value and it is greater than some value. This is what it means to be bounded.
Okay, sir. Got it.
Okay, so Dr. Mahadev, I'm not sure which graph you are talking about. So over here, this x is just your x value and y is your y value. So this curve that I'm fitting is
Yes, yes,
just
sir.
a function in one variable. This is just f of x rather than a vector because I can't plot it on paper. So I'm just taking one variable. So Akshay Bhargava asks why overfitting happens when too many parameters are there. Yes, so yeah, this is the precise reason why it happens is that this complexity of the function increases. So you can fit in many things. I think I missed one thing that I wanted to cover. Wow. Before going to decision tree, let me cover one thing that would answer your question also, Akshay. So I said that this linear regression are very powerful, but if you look right now, so these are just functions like this. So if I have, let's say I draw something over here. Let's say I have a curve like this. Okay. This is something, yeah, something like this. Now, if you will fit in any line, this will give you high error. Okay. Then why am I saying that this like this linear regression are very capable model? Okay. Now the reason is, let's say you have some feature like x1, x2, x3. Okay. Sanmitra Chatterjee, like bias variance, this trade-off I sort of explained in the last lecture. So if you go to this NPTEL thing, you have some recording sessions over here. So you can have a look at around last 5-7 minutes over there. Yeah. So let's say we have some x1, x2, x3. In this case, let's say we had some x and y. Now if we increase one more feature over here and we take x square. So you got, let's say 1, 2, 3. You got some y over here. Let's say 5, 7, 8, something like this. Okay. Now, if you took x square of these features, then what would you get is 1, 4, 9. Now, if you are taking a linear regression, including these two features, okay, what would happen is it would be something like ax square plus bx plus c. So what actually you are getting is a quadratic function. So in this parameter, like in this feature space only, if you increase the number of features based on this, like you take x square, if you had x1, x2, and then y, if you took x1 into x2, or something like x1 square into x2, then by increasing the features, what you are doing is you are making the functions more complex. And in this space, you are able to learn it using your basic linear regression techniques. Okay, so over the parameters that you get in this Akshay, in this linear regression is nothing but the number of features plus 1. Okay, so the number of features that you have, you will have one more parameter for the this like intercept that you have, and you will just have those many parameters. So the increasing number of parameters mean that you are increasing number of features, and features would increase something like this only. So that's why it leads to overfitting. Okay, I'll mm, sorry for this. Sorry for this disturbance. I'll just share again. Okay. So I'll quickly move to this decision tree because this was also covered. So I hope I made my point clear, Akshay. Yeah. Chats are gone. If somebody asked and I sort of missed it, so my chats are gone. You can type it. Okay. So for decision tree, I'll not go very deep into theory. I'll just take a basic example how to create a decision tree. I think that would cover most of it. Create a decision tree. Okay. So while creating a decision tree, we'll need two necessary ingredients. First is entropy. So entropy is taken from information theory, like people who study this kind of thing developed this first, and we are taking it from them. So let's say we have some data set. Okay, let's say we have this is our data set. Over here we have let's say 3 class. This is class 1, class 2, class 3, and this I'll have to put my laptop on. Okay. So I have 3 classes, right? Let's say these all classes are whatever data point we are getting are IIDs. Okay. So the probability of a data point coming from this class, let's denote it by P1, P2, and P3. So if we are picking a random data point, what is the probability that it will be from class C1 is P1? What is the probability that it will be from C2 is P2? And similarly P3. In that case, how we define entropy is just this summation. What we do over here is we take summation of, like this is number of classes, k is 1, 2, I is number of classes, P of k into log 2 pk. This is what we simply define as entropy. So let's say if we have a data set where there are 10 positive class data points and 10 negative class data points, then what entropy would get is, like, it would be minus, okay, minus at the outside. So probability of positive class is simply 10 by 20 because there are total 20 data points and we have 10 positive out of 10. So it is 1 by 2 log 2 1 by 2 plus 1 by 2 log 2 1 by 2. So what it is minus, this value is minus 1, log 1 by 2 is minus 1. So this is minus 1 by 2, minus 1 by 2. So the final value that we get is 1. So this is how entropy is calculated. So we have a simple question over here based on entropy. I encourage you all to do, this is based on the same formula, okay. So there are 64 data points, 29 belongs to class 1 and 35 belong to class 2. So probability of it belonging to first data set is 29 by 64 and P2 is 35 by 64. So this is a simple formula. You can use your calculators. Obviously, calculating log 2 value is not feasible mentally. So use your calculator and you can see like what values you are getting. So this is simply how it is calculated. Yeah. You can try, I'll wait for 1 or 2 minutes. You can use your calculators. Without calculator, it won't be possible in 2 minutes. Like at least if you have 2 classes, then your entropy would always be 1 if your probability is same. Otherwise, I don't think so. Yeah, in 2 class it would be. Otherwise also, let me see. So it is, no, it is not always 1, but yeah. It's nothing like stable or unstable. So like when you look at information theory perspective, what entropy kind of gives you, it's sort of negative of information gain that you're getting. So let's say you, yes, so 0.99 is correct. Okay. So if you look at like this example, when you had equal number of elements in both the classes, so even if you know that there are like equal number of elements in both the classes, you don't know anything new from it, right? So what I mean by that is, let's say you had 10 over here and 100 over here. Now what you know about the data set is, yeah. So what you know about this data set is that like it is very much biased towards the second. But if you had equal number of element in both the set, you don't know anything new about it. So anyone who is joining now, so this session would sort of end in 10 minutes or so. If you look at this NPTEL announcement, you will get another meet link. So another TA would be starting a session from 7 o'clock. I request you all to leave the session and join that one. Only those who joined right now in 1 or 2 minutes. Okay, now this is a formula for information gain. So there are a lot of questions on information gain in your weekly assignment. What is information gain? So in decision tree, what you have to do is you have to choose some attribute. Okay. You have to choose some attribute, and based on that attribute, you split your data set in some part. Okay. Now, if you chose an attribute A, then the information gain for that attribute is defined as entropy of your complete data set before you split anything, minus like a weighted sum of entropies of whatever you get after splitting. Okay, so whatever you obtain over here, you'll get a new data set over here. You'll get a new data set over here. So entropy of these need to be calculated separately. I'll give an example that I have prepared, not prepared, but yeah. So I'll give an example over here. So please read the question. So what it says is, elevation, road type, and split limits are feature, and speed is the target label. So target label over here is this. So we have two class, which is speed. Okay, whoever joined now, so this session started at 6 o'clock. It would end now. I request you to join the other session. If you go to NPTEL announcement, you will find a link over there.
So,
Yeah, yeah.
Pintu Kumar sir,
Huh, huh.
will you share that link with us, ma'am? Because
Uh,
at the end
so
of this session, I joined the session.
okay, so
That's
what
why.
you have to do is you go to NPTEL, where you have this course, swayam portal. Go to
Okay.
announcement section. You will see date plus time. So the time written for this one is 6 to 7. So there is another
No, sir.
session just below. Yes, yes, yes. If you just go below.
Time was 7 to 8.
So for 7 to 8, there is another link just below the time. If you'll see, I'll just share the uh, time with you. Don't worry. That link with you.
Will you share in chat box right now so
I'll
that we
share it.
can join?
I'll share
At
it with
least
you.
we can be on
Yeah,
time
yeah.
there.
I'll share it with you. Just a second. I'll share it with you. I have shared it in the chat box. So whoever joined like in last 5-10 minutes, please use this link.
Thank
Okay.
you, sir.
So wait, wait. Yeah, I've updated the link. The second one. Yeah. So yeah. So coming back to our example, so we have two classes, and it is saying that what is the entropy of this data set? Okay, so right now we have to just find the entropy. I'll skip this part, or we can just do the entropy part because there are two class over here, two class over here. It is same as the example that we discussed, 10 class here, 10 class there. So its entropy would be 1. So that is clear, and it would be useful for us later on. So entropy is 1. Okay. Now it is asking us to find the information gain if we split at the feature evaluation elevation. Okay, you see that elevation is of here. Yeah, elevation is here. So now if we look over here based on elevation, there are two possibilities. First is steep, another one is flat. Okay, now for steep we have two slow and one fast. Okay, and for the flat one we have one fast. So calculating entropy for this is very simple. It is just what it is, 0. Why? Because it would be something like probability of fast is 1, probability of second one is 0. So 0 times something plus 1 into log 2 of 1. So this is 0. So we'll get 0 over here. Okay. So I had solved this question earlier. So for flat it is 0, and for the other you can just have a look at this table that we have 2 slow and 1 fast. So probability for slow is 2 by 3, and probability for fast is 1 by 3. Okay, 1 by 3. So based on this data, we have this calculation. So I'm also using a calculator here. So we get entropy like this. So when we look at information gain, it is just 1 minus. So 3 of the data points were of steep type. So 1 minus 3 by 4 times entropy minus 1 by 4 was of type flat. So 1 by 4 times into entropy of that value. So this is how we obtain information gain. Okay. Right, people were joining. So this is how somebody's mic is on. Can you please turn it off? Yeah, thank you. So just a request, whoever joined late, the session started at 6 o'clock. So this would end in 5 minutes or so. I have shared a link in chat box. Please join that meeting. Some other TA is taking a session from 7 o'clock. Okay. So now this is how we had to decide upon the like how we had to calculate the information gain. Okay, now another type of question that you'll see in your assignment is, yeah, anybody has some doubt?
May I talk, sir?
Sure.
Yeah, there is one question, just like we saw, and it is asked that what can be the root of the decision tree?
Yeah, this is the question that I'm planning next. So this would answer your question. Okay. So
Okay.
here when you see labels are sad or happy, S or H. So 4 of them are S and 5 of them are this. Now when you have to decide upon the root of the tree, what happens is you will take the first attribute, let's say color. Okay. You'll find the information gain for this quantity. You will calculate information gain for color. That you can do, right? The way we did just before this, we will find the information gain for color. Then we will find the information gain for big. Okay. And at last, we'll find the information gain for number of years. So after finding out the information gain for all the attributes, we will see what attribute gave us maximum information gain. Okay. So whatever attribute would give us the maximum information gain, that we will use as the root node. That might answer your question now. So it involves some calculation. So you can do it definitely with the help of a calculator. So I tried doing it. I got color to be the most suitable choice for this one. Now, just to summarize how a decision tree work. Okay. So how does a decision tree work? Decision tree works. So first of all, you will be given with some data set, okay, along with some labels. So again, the first task over here would be to decide upon the root. So this is the first thing that we have reached. So let's say here I found out that the root is color. So based on color, okay, I'll again split this data set. So four of these data points goes as my over here. Okay, and other goes, so color over here is green. Then I have some blue. Then I have some red. So there are 3 branches that I got. Now forget about whatever we have built till here. Okay. After you have decided upon the root, forget whatever we built till here. What you have to do now is, yeah, based on the information gain, we'll decide upon the root of the decision tree, right? So whichever attribute has maximum information gain, we will take that as the root of the decision tree. Okay. So now what we will do is, we will look at this data set, this reduced data set that we have now, and we'll look at the information gain for this data set based on whatever splits are possible. And again, whichever split would give us the maximum information gain, we will choose that. Okay, this is how a decision tree is made. So I am done for today. So whoever joined in past 10 minutes, it's a request that this session has already ended. Some other TA started a session at around 7 o'clock. I am sharing a link with you. Please join that meet link to join that session. Others who were in my session from beginning, if you have any doubt about whatever I covered today, please feel free to ask. If you don't have any doubt, you can listen to others.
Excuse me, sir.
Yes.
In the next session, can you take one example, a complete example where we can build a tree?
I can take, if you want, I'll post it in the discussion forum, a complete example, because
Yeah.
next session would be something, I'll post it in discussion forum.
Okay, fine.
Okay.
And let me know whether recorded sessions of this problem solving are available.
Yeah, these sessions recordings are available. If you go to your course wherever you register on swayam, there is a section. I'll just tell you what's the name of that section. It's
It is, I
called
think, problem
problem
solving
solving
only.
session. Yeah. So if you go to that option, you will find a link to an Excel sheet. There all the these links are updated regularly. So you can find the recordings there.
Okay, thank you.
Surely if you want me to solve also, I can solve it for you, this information gain thing. If you see, we had this steep as well as flat. So we have to split on this elevation thing, right? So if you split on the elevation, you had three data points corresponding to steep and one corresponding to flat. Okay, so first thing that we split was on elevation. Okay, so
That problem is okay for the next problem. What you are explaining, root as color, root as color. For that,
yeah.
please show the information gain
Okay, so
values.
okay, right.
Information gain values.
See, if you look at this green, all the three
Yeah.
greens have the same label, right? So if you have same label, what do you expect the entropy to be? So if you have same value, like if you
Zero.
practice something, you will know straight away that it would be 0. Again, if
Yeah.
you look at the red, it has all the same values. So again, the entropy is 0 over here. Okay. Now, if you look at the class blue, then you have one positive label, one S label and one H label. So here you can straight away tell that the entropy is 1. Now the only task left is to find the entropy of this emotion. Okay. Entropy of this emotion. So whatever this complete data set, and then you have to take minus the fraction of blue 2 by 9 into 1. So this is what is that. I have calculated, I can show it to you. So the entropy of complete data set I found out to be this. So you can just simply use a calculator to do this. Another trick over here is, like when you're deciding upon the root, you need not actually calculate this, okay, this entropy, because at the end you are subtracting these quantities from this entropy. So whichever quantity is least, that would be your root, right? So whatever these are the entropy corresponding to color, entropy corresponding to wig, and entropy corresponding to number of years. So if your entropy is least, then your information gain is maximum. So you just calculate the entropies over here. So this is 3 by 8 into 0, 2 by 9, sorry, this is 9, 9, 9, so it would be 2 by 9, so this value would update. Yeah. So it was less when it was 2 by 8, so it would be even lesser when it is 2 by 9. So color would be the value when where would we split on. For calculation, this kind of calculator is good. So you don't remember all these log 2 values for sure. Anything else? No. So it is not necessary to always take last column as your data set. I'll come some into your question. So if you look at the question, the following data set used to learn a decision tree for predicting whether a person is happy or not. So whatever thing you want to predict, that is taken as your label for the data set. Based on that, you will find the entropy in those things. So it is mentioned in the question. I have not taken the last column as that thing, but it is mentioned in the question. That's why I took this last one. Okay. So which probability? Okay. So probability over here is, so I'll give you an example how I calculated the probability. If you look at, this is your data set, right? Now, if you look at number of people who are sad is 1, 2, 3, 4, and total number of people are 9. So what is the probability that a person is sad? It's simply 4 by 9. Okay. And for happy, it is 5 by 9. Now, when we look at just one class, like when we are looking just at the green class, then you look, all the 3 people are sad only. So then the probability of sad becomes 1 and probability of happy becomes 0. This is how I calculate the probability. Is it clear, Soman? It is, yeah, it is as simple as it. Like if you have a bag with 10 red balls and 5 green balls, what is the probability of a green ball? It is 5 by 15. Okay, I'll sort of end the